Hello, students. Good evening. Welcome you all for this third session on states of matter. Yes, till now we have mainly looked into macro study of gases and we understood what exactly is gaseous matter, right? And in macro study, we learned about gas laws, and then in last class we studied about Dalton's law, diffusion, and effusion. Right. What are the few gas laws that we studied? Uh, Boyle's law, Charles' law, Gay-Lussac's law, Avogadro's law, and finally ideal gas equation, which is combination of all the laws, which was PV equal to nRT. And we came across one more equation, right? PM equal to dRT, where D is density. Be careful, R can have multiple values based on what units you choose, right? Yes, then we studied about Dalton's law. Yeah, Dalton's law is what is the statement of Dalton's law? The total pressure is the sum of partial pressures of individual gases in the mixture of gases, isn't it? Yes, and then we looked into diffusion and effusion, and we also got the relation that rate is inversely proportional to root of density or root of molecular weight, and rate is directly proportional to pressure, and we combined these two, right? Today's class we will study about micro study of gases. Okay, so in micro study, we will look into individual particle, what are their behavior, and based on that, we will come up with few formulae, few definitions, few one theory, which is kinetic theory of gases. Right? Yes. Okay, and today's class also will be more of interactive because we will solve few questions based on whatever we are learning. So be active, participate, and kinetic theory of gas is heart of states of matter. Macro study, micro study, all depends upon kinetic theory of gas. So be attentive and try to understand kinetic theory of gases fully. Okay, yes. So when I take individual gaseous particles in any particular sample, okay, individual gaseous particles are in random motion, isn't it? We all know this because of thermal energy, gases are moving randomly here or there. Are all the molecules with the same speed they are moving? No, right? They are moving at random speed. Some are moving at very low speed, some are moving at very high speed. And what exactly is the pattern? That pattern is given by this Maxwell distribution curve. Okay, many natural phenomena follows this particular curve. Okay, this is called as Maxwell distribution curve. Fine. So from this Maxwell distribution curve, if I want to find out average velocity, right? What will be the average speed of any molecules that are just moving randomly here or there? Right? Why do we need that? To find out kinetic energy, isn't it? For finding out kinetic energy, we need velocity. So which velocity to take is the question, right? So there are three velocities. Most probable velocity, that means most number of particles. Here this is total, the fraction of number of particles. Here this is the velocity. Okay, so velocity versus fraction of total number of particles. So I can say half of the particles, let's say if there are 1000 particles, 500 particles are having this velocity. Okay, if delta n by n value is half, I can say it in that manner. If n equal to 1000, I can say that 500 particles are having most probable velocity. MP means most probable velocity. Okay, yeah, in certain cases we equate velocity of the sample as most probable velocity. In certain cases we approximate velocity to be equal to average velocity, and in some cases we approximate velocity to be RMS velocity. Got it? So these are the three velocities which we will consider. Note one thing, that most probable velocity is the least. Okay, you can see here, right? If I call this as V1, this has V2, this has V3. V1 is nothing but VMP only. V2 is V average and V3 is VRMS. So among this, V1 is least, that is VMP is least. After that, V average. After that, VRMS. Got it? So this one thing is always clear. Most probable velocity is the least. RMS velocity is the highest. Average velocity is in between. Okay. Now let us systematically try to understand how to find out most probable, how to find out average, how to find out RMS velocity. Okay. One thing is clear. Even if you are increasing temperature, what happens by increasing temperature? Thermal energy increases, right? Since thermal energy increases, molecules again will move randomly here there more vigorous, more faster, right? So that's why the number of particles that are going to have more velocity will increase. That's why the curve will follow this particular pattern. However, all types of velocity increase with increase in temperature. So if you look at most probable, initially it was here at T1, at T2 it is here. Okay, so most probable velocity has increased. Similarly, average velocity may be somewhere over here. At this temperature, it will be somewhere over here. And RMS velocity will be somewhere over here. At this temperature, it will be somewhere over here. So as a conclusion, I can say as I increase the temperature, all three velocity increases. So my velocity has some connection with the temperature, not just one. All the velocity have a connection with the temperature. Okay, yes. And based on this Maxwell distribution, I can find out total number of molecules in any velocity range. To plot a graph, I can use this formula to find it out, where n is total number of particles in collection, yeah, and m is molar mass of gas, T is temperature, U is starting speed, du is difference of speed, R is gas constant. By using this formula, we are plotting that graph. Okay. However, from competitive perspective, this has no weightage. Okay, this there is no question that is going to come on this. But however, this is just for your information that how are we plotting that Maxwell distribution graph. Fine. Yes. So now let us understand before going into that direct relation. We have got the hint that any type of velocity, if I consider, they increase with temperature, maybe square root or may not. Let's look into it little later. But let's try to understand how we are defining average velocity, how we are defining RMS velocity, and how we are defining most probable velocity. Okay, average velocity. It is the average of different velocities possessed by the molecules. Very direct, right? Average is u1 plus u2 plus u3 up to un by n. Or you can also consider weighted average. What does this mean? It's n1 number of particles out of total capital N number of particles. N1 particles are having u1 velocity, n2 number of particles are having u2 velocity, n3 number of particles are having u3 velocity, and so on. Then we call something as weighted average, which is n1 u1 plus n2 u2 plus n3 u3 dash 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 divided by n1 plus n2 plus n3 plus dash dash. Okay, yes. So this is about average velocity, which is most simplest one. Next, there is one more relation. As I said, U is directly proportional to temperature, which we have learned previously. And the standard expression for U average is root of 8 RT by pi m. So you can note this down. Questions come from this. Okay. In velocity type of question, this are the few formulas which are very important. Okay. U average is root of 8 RT by pi m. Next is root mean square velocity. What is root mean square velocity and how did that come? Okay. It is the square root of the mean of the squares of the velocity of different. What does that mean? Squares, I'll break it like this, square of the velocity. So if v1, v2, v3 or u1, u2, u3 like that, if is my velocity, then u1 square, u2 square, u3 square will be their squares, right? Mean of their squares. That means if I want to call weighted average, it will be n1 u1 square plus n2 u2 square plus n3 u3 square up to n number of particles. Okay, divided by n1 plus n2 plus n3. This is what weighted average of squares of velocity. Okay, what I have? It is the square root of the mean. So square root of this is square root of n1 u1 square plus n2 u2 square plus n3 u3 square dash dash dash. Here also divided by n1 plus n2 plus n3 plus dash dash. Okay, so this is what is RMS velocity. And how exactly, where exactly we use this? We use this to find out kinetic energy. And what is the basis for this RMS velocity? We know that kinetic energy is proportional to u square, right? So hence, to use some velocity, average velocity won't be a good approximation. Instead, whichever is having squares, weighted or squares, if that is there, that can best best used for kinetic energy. Clear? Yes. So this can also be written as root of 3RT by m. Again, the same logic. The URMS is directly proportional to root 3 and it is inversely proportional to molar mass. Obviously, right? If the molar mass, if the mass is heavier, the randomness will be less. Okay? So that's why it is inversely proportional to root m and directly proportional to root 3. Okay? And root of 3RT by m is the formula. This formula is something very important. You can note this. Yeah. Next is most probable velocity. What is most probable velocity? It is the velocity possessed by maximum number of molecules. So for any Maxwell distribution graph, it follows root of 2RT by m. Yes. So to summarize, U average is root of 8 by pi RT by m. URMS is root of 3RT by m. And UMP, U most probable, is root of 2RT by m. Okay. And what is the relation between these three? Sometimes directly questions come on relation. Okay. So they may ask you what is the relation of U average is to URMS is to, or UMP is to U average is to URMS. So in such cases, what we can do? The common factor, which is root RT by m, can be cancelled, and remaining thing would be root 2 is to root 8 by pi is to root 3. Isn't it? So on simplification, we'll get 1 is to 1.128 is to 1.22. This is one ratio, my students, should be clear of. Okay. 1 is to 1.128 is to 1.22. Sometimes direct question comes. When it comes, you can directly put this option. That's all. Okay. But make sure that it's UMP is to U average is to URMS. Yeah. If it is reverse, then this will also be reverse. 1.224 is to 1.128 is to 1. Yes. And what is the alternate formula for this gas velocities? In place of RT, I can put PV by N. Right? From gas equation, I know that PV equal to nRT. So RT will be PV by N. So I can put the PV by N in place of RT. Or we can write V by Nm as D. Okay. Nm is W by number of moles is W by molar mass into molar mass will get cancelled. V by W is 1 by D. Okay. That's how we get root of 3p by D. Clear? Yes. If you know this one, you can derive these two if any questions comes on them. And if you are not sure how to do that, then you can know this also. That's not a big deal. Okay. It's very rarely questions come from this type or this formula. Yes. Let's go into the question. Root mean square velocity of an ideal gas at constant pressure varies with the density as. What is the answer? Just now we did. Right? Yeah, what is the answer? It's URMS is inversely proportional to square root of t. Right? This is in some sense related to rate also. Right? Yeah, URMS is inversely proportional to square root of t. So I can say it's directly proportional. Varies with density as d power minus 1 by 2. Yeah. The formula was URMS equal to root of p by t. Yes. So using that we can say d power minus 1 by 2. Next question, by what factor does the average velocity of gaseous molecule increase when the temperature in Kelvin is doubled? Okay, when temperature is doubled, by what factor average velocity increases? So do we need to know formula? We need not to know formula. Only relation between velocity, average velocity and temperature is sufficient for solving this question. Okay. So what they are then telling? U2 by U1 equal to root of T2 by T. Because U2 is directly proportional to square root of temperature, right? So U2 by U1 equal to root of T2 by T2. So if say T2 is 2 times T1, they are doubling the temperature, right? So T2 is 2 times T1. So then U2 will be root of 2 T1 by T1 into U1, which is root 2 U1. What is root 2? 1.4. This is 1.4. What is the answer? 1 point. Got it? Yes. Yeah, you can expect such questions in exams. Huh? So you should be able to use this formula. Try to do this. If pressure of a fixed quantity of gas is increased 4 times, keeping temperature constant, the RMS velocity will be. Okay. Yeah, try to do it. Pressure is increased 4 times, keeping temperature constant. RMS velocity will be. What will be the RMS velocity? Yeah, I'll give you 2 formulas. You can use either of them, but tell me the answer. Let's see. Yeah, I said in the beginning, right? You have to involve in today's class. Yes, because this is one of the important topic of states of matter. Very important topic. Okay. Learn very nicely now, so that once the class gets over, you can revise and you can be thorough with the subject. Okay. Yes. Tell me the answer. Which formula to use? Which formula to use? And what is the answer for this? Yes, anyone? Anyone? What is the answer? 4 times, 2 times, same, half time. Yes. Yes, what is the answer? Quick. I'm expecting your answer to be 2 times. Let's see. Yeah? What is the answer? What is the answer? Option 1, 4 times. Yeah, it's not 4 times. It's same. Can anyone tell me how it will remain same? How it will remain same? It's not 4 times. It's same. How will it remain same? How will it remain same? If you read the question, it says if pressure of a fixed quantity of a gas is increased 4 times. Okay. If it is increased 4 times, keeping temperature constant. So that is the key thing over here. So you are increasing pressure and you are maintaining temperature constant. What does that mean? What does that mean? Yes, volume has to change. Okay, so when you are increasing pressure, keeping temperature constant, then it will follow Boyle's law. Pressure is inversely proportional to volume. So, or I can say PV will be equal to constant. Yeah. So if I look at formula 1 or formula 2, PV is constant as per formula 1 or temperature is constant as per formula 2, right? So in both the cases, I can conclude that URMS is not going to change if you are increasing pressure but not increasing temperature. Got it? Yeah, you can reply. If you have understood, please reply. Okay, it's just same. Okay, because temperature does not changes. Pressure increases, but as whole, pressure and to volume will remain constant because you are keeping temperature constant and you are increasing pressure. So it will follow Boyle's law, that is PV equal to constant. Understood? Yes. Yes. Yeah. So the answer is it will remain same. Try out this. At what temperature RMS speed of H2 is same as RMS speed of O2 at 400 Kelvin? Yes. Quickly answer this question. What is the answer for this question? Yes. What is the answer? What is the answer? Yes. What is the answer for this question? Which formula to use? Again, same thing. URMS equal to root of 3RT on M. Yes. So they are telling URMS of H2 is equal to URMS of O2. So these are the two things that we know. From this, can you find out at what temperature these two will become equal? At what temperature for hydrogen these two will become equal? Yes. What is the answer? What is the answer? Yes. Any answer? Yes. What it is? Yes. Apply it in formula. Yeah. So I can write 3R TH2 divided by MH2 equal to root of 3R TO2 by MO2. Right, that's what they are telling us. RMS velocity of both of them are same. And TO2 is given to us root of 3R I can cancel out on both sides because both are going to remain same. MH2 is I already know. MO2 also I already know it. Right. Molecular weight of H2 is 2 and TH2 will be there. That equal to molecular TO2 is given as 400 divided by molecular weight of O2 is 32. Yes. So when we solve this, what will we get? Root of TH2 divided by root of 2 equal to root 400 is 20. Root 32 is, it will be 4 root. Okay. So root 2 cancel. 4 ones are 25. 4 5s are 20. So TH2 will be square of 5, which is 25 Kelvin. Got it? So answer is first option. Okay. Yeah. Answer is 25. Okay. Next, we will look into most important topic of states of matter, which is KTG, Kinetic Theory of Gases. Okay. What is Kinetic Theory of Gas? It is theoretical model which can correlate the experimental facts. Okay. It was put forward by Bernoulli and developed by Clausius and Kelvin. Okay. It was explained by Maxwell and Boltzmann further. Okay. Yes, there are few theories, few are assumptions, few are postulates. Okay, and these postulates govern various laws. Okay, using this postulate, we have cross-verified various gas laws: Boyle's law, Charles' law, Gay-Lussac's law, Avogadro's law. That's why I was saying kinetic theory of gas, sorry, is uh, important both for macro study as well as micro study. Okay, few of the postulates are: gas consists of small particles. Yeah, what do you mean by this small particles? They don't have any interaction with each other. Okay, molecules or atoms identical in size, shape, and mass. So they are considered as small individual particles. Okay. Second postulate: the volume of molecule itself is considered negligible with respect to total volume of the gas. Okay, so yeah, to give best example of this, if you are able to relate, I'll give you one example. H2O, when it is in liquid form, when it is in liquid form, 1 mole of H2O is 18 grams, right? 1 mole is 18 gram of H2O. So 18 gram of H2O, if you just remember, the density of water is 1 gram per cc. So 18 gram will have 18 centimeter cube volume. However, when the same H2O is getting converted to vapor, getting converted to gaseous form, then 1 mole will have 22.4 liter. If I want to write it in centimeter cube, it will be 22,400 centimeter cube, which is much, much, much higher than 18 centimeter. That's why we ignore volume of molecule itself. That means if you only consider molecule, their volume is very negligible compared to total volume. Okay. Yeah. Third point, there is no force of interaction, attraction or repulsion between the gas particle. Okay. That is, each molecules move independently. Yeah. Because of this only, we are able to apply various gas laws. Okay, we assume that there is no force of interaction between any adjacent molecules in gaseous state. Okay. Fourth one, the gaseous molecule move in rapid motion. We all know that, and collide randomly with each other as well as the walls of the container. Okay, so molecules, if you can take them in one container, gaseous particle, they will just move randomly here, there, and they will also hit all the walls of the container. And that hitting creates pressure. Okay, the pressure of gas is due to the collision of molecule with the walls of the container. Okay, fifth postulate: the collisions are perfectly elastic in nature. Yes. So if it was not perfectly elastic, then what would have happened? Energy loss would have taken place, right? Gases are moving randomly here, there, and they are colliding with each other also, isn't it? So if they are colliding and losing energy, one time may happen that all gas particles come down, but reality is not that, right? They are just moving randomly here, there, and nowhere there is loss of energy. That's why we assume that the collisions are perfectly elastic in nature. There is no energy loss. Hence, there is no net loss of kinetic energy. Kinetic energy can be transferred from one molecule to another, but it is not converted into any other form of energy. Okay. So total kinetic energy at any particular temperature remains same. That's what even sixth postulate continues, that at any instant, given molecules can have energy range. Few molecules will have less kinetic energy, few molecules will have more kinetic energy. But when you find average, okay, average kinetic energy of the molecule, which is half into m into v RMS square. This happens to be the velocity that we consider to find out average kinetic energy. Okay. Because average kinetic energy means what? Altogether, it is half mv1 square plus half mv2 square plus dash 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 up to half mvn square, right? So these are individual masses, and when I take all together, the mass will be nm. If there are n particles will have altogether nm mass, right? So average means whole divided by n, right? So half m, if I take out, this whole part which is remaining is indirectly only representing RMS, right? We already know that. So this factor which is there, this is nothing but VRMS square. That's why for to find average kinetic energy, we directly use VRMS square, which is actually found out by using average kinetic energy only. Okay. Yes. Seventh, the law of classical mechanics are applicable to the molecules. Why? We assume that there is no force of interaction between molecules. That's why we can apply law of classical mechanics over here. Okay. So now there is something called as collision frequency. Because the molecules are colliding, there are related terms to it. It is equal to the number of collision occurring per unit volume per unit time under the specific condition. That is called as collision frequency. And there is something called as mean free path, which is the distance covered by the molecules between two successive collisions. Yeah, that is free path, and mean of all such free path is mean free path. Yeah, this is just the side information for you all to know. Okay. Yes, so lambda, it is denoted by lambda, which is given as kT by root 2 pi sigma square P. The sigma is diameter of the molecule, P is pressure of the gas, T is temperature in Kelvin, and K is Boltzmann constant. Yeah, yeah, this is just the side information which you all can just know this. In general, lambda is proportional to T. This one thing you can know, lambda is proportional to T and lambda is inversely proportional to P. Mean free path is inversely proportional to pressure of the gas and directly proportional to temperature. Okay. Yes. So next, using kinetic gas equation, kinetic theory, let us try to get this kinetic gas equation. Okay, which is PV equal to 1 by 3 Mn URMS square. Okay, and we know that 1 by this Mn URMS square is in some sense representing kinetic energy, right? Yes. So basically, when I consider a Q, I'll just give you a brief explanation on how exactly we find out PV. Okay, PV is the total work done, yeah, which is distributed in all three directions, above to horizontally and towards and away, right? And there are total number of particles, which is m into n, mass into number of particles will be total mass, yeah, into URMS square is the total work done by the system, by that system, which is equal to P into V, pressure into volume, right? But if I want to consider in only one direction, that will be 1/3 of it. That's how we got this expression, PV equal to 1/3 into Mn URMS square. PV is work done, and that is 1/3 of in one direction. Okay. Yes. But now if I go on simplifying it further to get kinetic energy, then I can yeah, these are all just the steps. Yes, what I can do is Mn URMS square, because I have already used, I can tell Mn URMS square into 1 by 2 into 2 by 3, right? This is equal to 1 by 3 into Mn URMS square, which is 2 by 3 into 1 by 3, 2. Yeah, because why am I dividing and multiplying it with 2? So that this will represent kinetic energy, right? So 2 by 3 kinetic energy equal to PV. That's what it means. Okay. So that's what we are obtaining here also. Kinetic energy equal to 3 by 2 PV, right? If I move it to other side, or PV is nothing but nRT, so I can write it as 3 by 2 nRT. Okay, this you need not to get afraid of all of this. This is just the same thing, okay, which we already did in case of kinetic theory of gases. Okay. Yeah. Okay. While discussing kinetic theory of gases, I have already shown you that in place of using U1 square plus U2 square, in place of using this as average kinetic energy, I can directly take average kinetic energy as half mn URMS square, because URMS represents for average kinetic energy. Okay. Yes. So this expression kinetic energy equal to 3 by 2 nRT is again important, and this also is important. Kinetic energy equal to 3 by 2 PV. Okay. Yeah. Similarly, we can also obtain equation for RMS speed using this. It's quite direct, right? See here, PV equal to 1 by 3 into Mn URMS square. Mn is also molar mass into number of moles. Yes. So I can write it as mass of gas, which is n into molar mass, right? So yeah, okay, we can do it either this way: nRT PV equal to nRT by mass of gas, or yeah, instead of doing it this way, let's take it this way: PV equal to 1 by 3 into n into molar mass. In place of mass of gas, I am just putting number of moles into molar mass, which is also mass of gas, into URMS. So if I take Nm to the other side, it will be PV by Nm, and 3 I'll take to the numerator, it will be 3 PV by Mn equal to URMS. And we already know URMS is nothing but this only, root of 3 PV by Nm. Or I can write in place of PV by N as root of 3 RT by M. So this is what they are also trying to get it, using N first, so that mass of gas will get cancelled. RT by M will be remaining on the other side. 3 I can take to left side, will become root of 3 RT by M. Okay. Yes. So this is few of the application. So as we saw in the previous case, over here, kinetic energy is 3 by 2 PV, and we also know that kinetic energy is proportional to temperature, right? Yeah, so kinetic energy is proportional to temperature. So by using this kinetic energy equal to 3 by 2 PV, I can also say 3 by 2 PV, because kinetic energy is some constant K into T, right? Because kinetic energy is proportional to temperature. We heard, right? The kinetic energy increases with temperature. So I can say kinetic energy is proportional to temperature, or kinetic energy equal to kT. So I'll put 3 by 2 PV equal to kT. So PV is again equal to 2 by 3 kT. So this 2 by 3 kT in some sense representing some constant. So we can get ideal gas equation also using kinetic theory of gases. So understood. So we can do macro study also, we can get ideal gas equation also, and we can get RMS velocity, which is micro study. Okay. That also we can get using kinetic gas equation. Okay. So this is about the kinetic theory of gas. Okay. Yes. So to summarize, we studied about, in the beginning we studied about URMS, U average, and most probable. And which one is maximum? URMS is maximum, U average is middle, and U most probable is minimum. Okay. And the expressions are, for most probable, it is root of 8 RT, sorry, 2 RT by M, and U average is root of 8 RT by pi M, and URMS is root of 3 RT by M. Okay, and then the ratio, which is very important to be known. Okay, ratio is very important, and if you know these three formula, major part of it is done. Okay, in velocities. And then we learned about kinetic theory of gases. So in kinetic theory of gases, there are altogether 7 postulates or assumptions, and all of those assumptions will indirectly give me the expressions for ideal gas equation also and RMS speed also, right? Kinetic energy expression also I can get using this kinetic theory of gases, right? Yes, and then we looked into how PV equal to 1 by 3 mn URMS square, and from there we obtained expression for kinetic energy as well as um, RMS velocity. Okay, kinetic energy, important expression is 3 by 2 PV, or I can also say kinetic energy is 3 by 2 PV. In place of that, I can put nRT. So this is about this whole part of microstructure. Okay. Yes. So we'll end here. Hope you understood this. Okay. Thank you.